Okay, we're going to get started today. Welcome everyone. My name is Will Burns and I serve as director of the Forum for Climate Engineering Assessment at American University. I'm joined also today by the forum's director of research, Dr. David Morrow. The forum's overarching purpose is to generate a dialogue on a potential suite of responses to climate change that are often characterized as climate geoengineering, as well as options often referred to as carbon removal or negative emissions technologies. This is the second of the forum's hour-long webinars in a series devoted to carbon removal negative emissions technologies. To access the first episode in this series, which provides an overview on this topic, or to view other resources on carbon removal and negative emissions technologies, please visit our website. The address is ceassessment.org. Today's webinar will focus on 3 recent pieces that were published in the journal Environmental Research Letters. This research constituted an effort by 20 researchers at 10 different institutions to conduct a systematic review of negative emissions technologies on a number of different axes. These include the current status of research, potential ethical considerations associated with deployment of various negative emissions technologies, and suggestions for how to spur innovation in this field, as well as potential upscaling of research and advancement of utilization. We're pleased today to have the 3 lead authors of these pieces with us, and I'd like to briefly introduce them. Professor Jan Minx, who is with the Mercator Research Institute on Global Commons and Climate Change in Berlin, as well as Professor for Climate Change and Public Policy at the Priestley International Center for Climate at the University of Leeds. Second of all, Dr. Sabine Foose, who serves as the head of the Working Group on Sustainable Resource Management and Global Change at the Mercator Research Institute. And finally, Professor Greg Nimet, who serves as an associate professor at the University of Wisconsin-Madison in the La Follette School of Public Affairs and the Nelson Institute Center for Sustainability and the Global Environment. Welcome to all of you and thank you for participating. Initially, I've asked each speaker to set the table for us today in terms of these articles by presenting respectively 5-minute summaries of the articles that they co-authored. I'd also like to note that if you'd like to pose a question to any of our speakers, you can use the chat functions. At the end of the presentations, we'll get to as many of your questions as we can during our hour together. And if there's a lull, I will also present some questions to the respective speakers. With that, I'd like to turn to our first presentation by Professor Minx on the article that he served as lead author for in the ERL collection, which is entitled Negative Emissions, Part 1, Research Landscapes, Ethics, and Synthesis. Dr. Minx?
Thank you so much. I just need to... Can you see my presentation?
Yes.
Okay, excellent. So thank you so much. It's a great pleasure to be here. First of all, as already highlighted, even though there are 3 speakers here, this is an effort of many people, and you see the names here, and all of these people have really contributed significantly to this piece of research, which I will now introduce to you. So, as it was already mentioned, we basically did a 3-part systematic review on the literature of negative emissions. I myself, and I will served as a lead author of the first part, which basically focused on the research landscape on negative emission technologies, but also the literature on ethics and a synthesis of the overall project with all the information coming from parts 2 and 3. The the second part, led by my colleague Sabine Foose, basically addresses the literature, what we know about the cost potential of side effects of the various negative emission technologies. And the third part, led by Greg Nimet, focused on innovation and upscaling. When we said we did a systematic review, it was really important for us to comprehensively cover the literature that is available. So we basically defined a transparent and reproducible search query, and we searched the Web of Science and Scopus. We also reached out to many individuals to ask for additional publications. That effort yielded just over 6,000 documents. We took that and then did a preliminary Scopy review where we tried to identify a core set of articles that we transparently describe based on inclusion and exclusion criteria for each technology cluster. That yielded about 2,000 documents, which we then analyzed in part one in terms of the scientific landscape. In part two, we further boiled that literature down and extracted information from about just over 900 documents that yielded informations on the technology's cost potential and side effects. And in paper three, we basically coded each of the 2,000 documents in terms of innovation stages. And on papers 2 and 3, you will get some further details in subsequent presentations. So how does this research landscape look? It's rapidly growing. So the research on negative emissions is actually growing faster on average than literature on climate change itself. But it's also really diversifying, and that is also kind of well represented in IPCC assessments. So basically the first 3 IPCC assessments mainly focused on biological sink enhancement, and you see there that this is actually a good representation of the literature that was available at the time, and this was all still covered by the definition of mitigation. But if we consider those as nets, we also really learn that nets, are not something new, but are, or at least some of the nets are part of a long standing discussion on solving the climate problem. AR4 then first introduced the term negative emissions that came along with some integrated assessment modeling scenarios that included BACs. And in AR5, we have a real diversification, and all major nets were actually discussed in the Working Group 1 and 3 report. In AR6, we don't know yet, but I think for the 1.5 special report that is upcoming in autumn, we can expect some pretty comprehensive treatment of negative emission technologies. So, and one important question we looked at was, in terms of the scenario literature, what can we learn about the role of negative emission technologies for reaching the climate goals? And it's very instructive to compare 1.5 and 2 degree scenarios. So if we focus on 1.5 scenarios, we really see in our scenario sample that those are basically fully decarbonized already by 2050 through sharp emission reductions, and that is then followed by a sustained period of deep net negative emissions thereafter. And therefore, for 1.5 scenarios, we see actually a much more rapid upscaling of negative emission technologies and high deployments already in 2050, up to 15 gigatons. But most importantly, in terms of comparing 1.5 and 2, is that actually we did not find any evidence, any 1.5 scenario that can do it without. That led us to the conclusion that there are indications that they are already geophysically dependent on negative emissions, while 2 degree scenarios in principle could still do it without at least under fairly extreme assumptions. And given the importance, and we have 5 minutes here, so I'll close on this. It's really important for us to highlight that in this discussion of how to frame carbon dioxide removal or negative emissions, that we think it's very unfortunate that it's framed alongside geoengineering. CO2 removal really addresses the causes of climate change like mitigation, while solar radiation management basically is focusing on the symptoms. And also the kind of risks involved are very different, where we believe that in terms of CO2 removal, we actually know from other mitigation measures about them pretty well, while in solar radiation management, they are quite different. Therefore, we basically try to strongly express our view that we should have actually a fourfold distinction on human response actions, where we have mitigation and adaptation, and basically flank them with CO2 removal and solar radiation management, but not mix them up, because those loaded discussions on solar radiation management actually may also hinder some political momentum for CO2 removal that is actually urgently required if you look at the scenario evidence. And with that, I'll leave it. Thanks so much.
Thank you very much, Jan. And with that, I'd like to now turn to Dr. Foose to summarize the article that she lead authored in the ERL collection, which is entitled Negative Emissions Part 2, Costs, Potentials, and Side Effects. Dr. Foose?
Yes, can you see my screen?
Yes.
Yeah, okay, perfect. So thanks a lot for this kind introduction and for having us. So as Jan was already introducing, I am going to tell you about part 2, where we were focusing on the costs, potentials, and side effects. And again, you see this large amount of authors as well that were all contributing very significantly to what I'm just going to show you right now. So starting off with the costs, these are 2050 costs, and of the almost 1,000 papers that were left in the scoping process that Jan was already showing, we pulled out the information on costs, potentials, and also side effects. And what you see here are heat bars. So wherever the color gets redder, that's where you get the most agreement between studies for certain estimates in the cost spectrum. All the different bars, these lines, these black lines, refer to ranges in the studies. So for afforestation, you see quite some agreement on the lower end, indicating that these will generally be less expensive per ton of CO2 removed, a little bit higher for bioenergy combined with carbon capture and storage, less evidence actually at the global scale for biochar, and then also technologies where we have more dispersion, where we have actually not only wide ranges within studies, but also across studies we see a quite scattered amount of evidence. And that is because there are also different underlying assumptions if you look at the bottom-up literature. For enhanced weathering, similarly, and ocean alkalinization. And for soil carbon, actually only one study that really fixes a global cost level. Now, if you then look at 2050 potentials, you see actually more agreement in the sense of that for all of the technologies that we looked at, we identify significant potentials. Except actually for ocean fertilization, even though you see 16 studies here, because here we are actually partially also because of the de facto moratorium on implementation of ocean fertilization coming from the London Protocol, having more theoretical studies and less evidence at large scale. And all the different dots that you see are actually different studies that we looked at. And you actually see that here we also diverge quite a bit between the different studies. So what we actually did then, in order to provide a little bit more useful information, is that we invited 2 experts at least per technologies to join the author team and to look at the assumptions behind the different studies in order to boil down the potentials and cost estimates to something more narrow, based also on what we learned about the side effects that I'm going to show you in a minute. So this is actually what you're seeing here, where we plotted costs and carbon removal potentials, and where you see confirmed that the more natural based ones, afforestation, soil carbon sequestration, biochar, are on the less costly side, and then direct air capture, carbon capture and storage on the more expensive side. But even there we see costs coming down, as you saw actually in David Keith's recent study that has not been part of this systematic review yet. So I'll use my last 2 minutes on the other aspects that we assessed in paper 2. So for all the different technologies that we're looking at, the technological readiness, side effects, and permanence. And since I cannot go through all of them, I just focus on 2 that have been most prevalent in the scenarios that Jan was just showing: afforestation and reforestation on the one hand, and bioenergy and carbon capture and storage on the other hand. And you see that both actually are associated with a high land footprint, and therefore could have potential negative side effects. At least these are mostly identified in the literature that we looked at, for preservation of biodiversity, but also securing food supply. Then if you look at the technological readiness for afforestation, reforestation, we're looking back at a lot of experience with these techniques. So this would be ready for larger scale deployment, whereas for BECCS, we really only have 1 full-scale demonstration plant at the moment. And finally, on permanence, geological storage, associated with BECCS, is generally in the literature regarded to be more stable, whereas for afforestation, reforestation, it's of course, the carbon storage is of course subject to human interventions, to climate events, and so on. So this is reversible, and the carbon could be more easily released. So with that, I want to close, but I'm happy to have a discussion later on.
Great, thank you very much, Dr. Foose. And then finally, I'd like to ask Professor Nimet to summarize the article for which he served as lead author in the series, which is entitled Negative Emissions, Part 3, Innovation and Upscaling. Greg?
Great, thanks. Can you see my screen here? It looks like it. Okay, great. So in Part 3, we're focused on the innovation and how you increase the scale of negative emissions technologies. And what we really tried to do was 3 things. We wanted to look at the integrated assessment models and look closely at the timing of deployment. So when nets and how quickly nets would be assumed to be deployed. That was 1. 2, we looked at the innovation literature, so in general, not just on nets, to see what it said about scale up and deployment and the timing of that. And then 3, we coded each of the articles that Jan mentioned at the beginning, the 2,000 or so nets articles, by the stages of innovation that they represent. So I'll show some data on that, but you could think of an article being considered research and development, or an article being considered something about demand for that technology. So I'll talk about that in a minute. So with those 3 questions, then we asked, are they aligned? Is the scale up assumed in the integrated assessment models aligned with what the innovation literature says and what the nets literature is focusing on? And the short answer is no. So let me just kind of give some of the summary results of this. So we coded these 2,000 articles. We found that overwhelmingly the focus is on articles that we would consider research and development, and even more overwhelmingly 83%, are really focused on the supply of innovation. And I'll talk about that in a minute. And much less was talked about the demand for nets, like who would actually want nets, who would adopt them, how people might react to them on large scale. And there's very, very little on that. One striking aspect we found from looking at the integrated assessment models is how imminent the scale up is. So we're talking about hundreds of megatons of new removal capacity. So not just removal, but new nets capacity being installed every year, really starting in 2030 to 2050. So even though nets are often talked about as the second half of the century, they are in terms of removal, but in terms of actually deploying the technology, it's much sooner than that. One of our key takeaways is that we're lacking, the literature is really lacking an analysis of demand for negative emissions technologies. And then when we looked at individual technologies, BECCS was slightly above average in terms of talking about markets and who might want to adopt nets. And direct air capture was well below that. So that seemed like a really a key hole in the literature, is who would actually adopt and want to have direct air capture technology. One of the kind of more qualitative aspects we saw was that nets are almost exclusively talked as being deployed. It's really almost a military metaphor where we think about putting lots of those technologies out there potentially very quickly, whereas the innovation literature talks about technologies being adopted, where people choose to want to use that technology, to pay for it, to use it, or to even put up with it if it's nearby. And so that seems like a shift that we haven't seen yet that'll have to happen. The literature really doesn't reflect the urgency that's in the integrated assessment models. And then I think one of our key takeaways is that given what the literature says, what the innovation literature says is needed, and what the NETS literature already contains, we need a much bigger effort on post R&D innovation. So things like early deployment of technologies, development of niche markets, scale up processes, and then a lot on demand and public acceptance. So those are the key takeaways. Maybe just for the last couple minutes, I'll just show a bit of the results. This is coding the different articles by the stage of innovation. And I guess I won't go into detail now, but just to show that more than half of them we would code as research and development. But these other 5 categories are really needed for innovations to be successful. And if you look at the innovation literature, it talks about successful innovations are ones that connect a technological opportunity with a market opportunity. And I think what we're seeing in the literature is a lot of effort on enhancing the technological opportunity and really not enough on developing the market opportunity. And so that's kind of what our data say from looking at the coding the different articles. And then just to try to pull that together in this graphic here in the top panel, you see the deployment assumed. So here is where we're talking about negative emissions in the level of gigatons really kicking off in 2030 and some more stringent scenarios before that. And then we look at the literature, you would expect by now, if we're going to have large scale deployment, within a little bit more than 10 years, we should be seeing a lot of demonstration projects starting to be seriously addressing niche markets. And I can talk more about those maybe later. And then just a lot of discussion about where the demand will come from and how people will react to them. And that's where we see not enough work being done. So that's where we need more work. Just in maybe the last minute here, one of the things that seems to be emerging, and this is kind of emerging ideas from this work, is that it seems like the nets are different from each other, and that maybe you could think about 3 categories of nets that have different analogs. So maybe I won't take the time to go through all of these, but we have some that are kind of high technology that might have a lot of repeated processes that might be similar to how electric vehicles or photovoltaics have been developed. So DACs could pursue a similar road. Some of them are low tech and not very distributed, lots of actors involved. Things like soils, where you've got maybe billions of farmers involved, and that looks like something not like solar or electric vehicles, but something more like hybrid seeds and the green revolution. And then third, then we've got these large scale, industrial scale technologies like BECCS, where there's a kind of a natural aspect in terms of where the feedstock comes from. And that may be more similar to something like a chemical plant or a refinery. So I think we need different models for these different types of nets if we want to accelerate, if we want to have more innovation in them. And then finally, on the last slide here, one striking thing is that if we're talking about this deployment starting in 2030, we need to do all of this accelerate the process of innovation much faster. And one example, if we take from the last slide, if we think that DACs could pursue something similar to the success of photovoltaics, we should look at how long it's taken photovoltaics to really become low cost and eventually disperse widely. So the first demonstration plant for PV was a satellite in the late 1950s. I think 2017 is when we really had solar beating fossil fuels without subsidies. And then if you look at models of more than 10% of energy supply, then we're talking 2030s, 2040s. So that's a pretty long time period. So if we apply that to DACs and say the first commercial DACs deployment was in Switzerland last year, then that takes us out to the very end of this century for low-cost DACs and widespread adoption of DACs, and that's far too late. So what we need is some kind of accelerated model where we have low-cost DACs much sooner than that, like in the next decade, so that we're on the time frames that the integrated assessment models say we need to be, and that means everything has to move a lot faster. So that's kind of subsequent work now, is to think about how you could accelerate. So I'll stop there.
All right. Thank you very much, Greg, and thank you to all three of you for excellent summaries of the respective articles. And it's rare among academics when you ask them to speak for a prescribed period of time that they actually do. But you all did, and I greatly appreciate that, because that should facilitate a lot of productive discussion and questions. And so what I'd like to do initially is have David Morrow, who's our research director, field any questions that have come across the virtual transom from those that are participating in the webinar, and then I will supplement it if we have time with some questions that arose in my mind from reading those three pieces. So, David, are there initial questions from the audience?
There are, and if audience members have additional questions they'd like to submit, they can use the chat function in their GoToWebinar control panel to send them to us. To get started, we've got a cluster of questions that I think are best addressed to Jan, but Sabine and Greg might jump in with some input too. They have to do with scenarios that do not involve nets. So let's start with the 2-degree scenarios. Jan, you mentioned that some of them don't use CDR. Can you tell us a bit more about how many of those scenarios there are, and what are the assumptions behind them? What has to happen to get to 2 degrees without nets in those scenarios?
Yeah, I think in AR5, the novelty in the integrated assessment scenarios is that they basically did some sort of sensitivity analysis. What actually happens, if policy is delayed when policy is more fragmented, then rather assuming, an adequate global carbon price immediately. And the second dimension was that they tried to see, what's the importance of certain technologies. And BECCS, for the first time in AR5, was added as a negative emission technologies in most of those scenarios that was available for assessment. And one of these tech constraints was, not having CCS. So it's actually more than not having BECCS, but of course it includes not having BECCS. And what you could see in those scenarios is that the likelihood of scenario runs to fail increased. So not as many models could actually do the job anymore for reaching 2 degrees. So highlighting, that it gets much more difficult. But on the other hand, it also showed that even in the absence of such a technology, those scenarios could still do it. But of course, they had to do it by, much faster reducing emissions, particularly in the first half of the century. And I think that's a kind of a typical thing. in terms of, how do we judge that? I mean, many people, have concerns that IAMs are anyway very, optimistic about, institutional change that is required and that we are far away from that. And of course, that's the case. And we are now even seeing 1.5 scenarios where they try to limit, the negative emissions deployment with all sorts of radical assumptions about lifestyle change, etc. And, to me, it's kind of interesting exercise to see, how much carbon are we actually already committed to? Because essentially, it's comparing a carbon budget versus a carbon commitment from our energy system infrastructure mainly, and that's an interesting exercise. But above all, I believe, we are far away to see anything that is actually only nearly described in those models. The only trajectory we actually can follow is the baseline, right? So we are far away from any trajectory that even in the 2-degree world, limits NET's deployment. For that, we would need to see radical action, and sustained and rapid emission reductions, and we are not seeing this. So we are, if we are going to meet even the 2-degree targets, I believe that we are moving certainly into a high negative emissions world. But that's a personal opinion, of course.
Sabine, Greg, did you want to add anything on 2 degrees?
I don't.
Sabine, we can't hear you. I think you might be.
Yes, I got muted. Sorry.
Thanks.
Yes, actually coming a little bit from the side of my paper, I would also ask myself, why are we actually asking ourselves this question? Like, why would we want to achieve 2 degrees without negative emissions? And if the motivation is in the side effects, for instance, the large amount of land that we would need to cultivate the biomass for bioenergy of the BECCS chain in those scenarios, then we also have to see what actually happens to those indicators in those scenarios where we actually constrain CCS. And what you actually see in many of those scenarios is that you use a lot of bioenergy, because BECCS is often used to offset difficult to decarbonize emissions in other sectors. I mean, think of non-CO2 GHGs in the food system. Think of air travel. If we would do that with biofuels, then we are actually no way better off than with the biomass that we cultivate for a BECCS chain. So I think if we're asking these questions, we also have to keep track of why we're asking them and to see what are the alternatives.
Okay, let's talk about a more ambitious target then. So Jan, you said in talking about the 1.5 degree target that all of the scenarios you look at include nets. And we've got a question here about the more recent scenarios. I assume this is about Detlef van Vuren's paper about how to achieve the 1.5 degree target without using nets. How do the results of that paper sit with the results of yours? Is that included in your literature review?
I mean, the paper, of course, is not included. It was published after, our literature cutoff. But Detlef, I think, is really misunderstood, because he's not saying we are doing it without. He's trying to limit the use of nets, right? So he can limit the use of BECCS in particular, but there's also afforestation. So they have a much smaller uptake of negative emissions than you will see in many scenarios. But equally, the study by Arnulf Grübler and the study by Holz, which also came out recently, Holz even claims it's a no CDR scenario. But if you look into the table, you will see that this is a matter of to my understanding of declaring what's a negative emission, because they have a category which is like net emissions from land use change, which then becomes substantively negative, and even make sure that you have a net negative budget in the second half of the 21st century. Of course, there is no large-scale BECCS there is no large-scale afforestation. That's all true, but there is still more than 150 gigatons of negative emissions. But above all, I want to re-stress the point made before. We can have all sorts of academic exercises, right, in terms of now finding out how radical we can be in our assumptions to, you know, essentially to limit the amount of residual emissions we can think of. But I perceive the world we are living in to be far off such exercises.
Okay, let's shift gears here a little bit. We've got a question addressed primarily to Greg. Do you think the concern about moral hazard is a barrier to investment in nets beyond this basic R&D that you said most of the papers are focused on?
Well, I think the moral hazard argument would say that the existence of nets would be a barrier to investment in R&D and mitigation. I think that is kind of the direction of what people talk about with moral hazard. That's why people are concerned about that we're even talking about moral hazard, or that we're talking about negative emissions. I suppose then, but if you are so concerned about moral hazard that you say we shouldn't even be doing R&D on it because it'll deter people's efforts at mitigation, you know, I guess that's kind of where the question is coming from. I don't know. I mean, I feel like, you know, we need to be doing a lot more mitigation, a lot more research and further innovation activities on nets, and, you know, looking into solar radiation management as well as funding adaptation. So I don't, to me, the most likely successful scenario for dealing with climate change overall is doing all of these things to some extent. And so I find it a little bit, I don't know, I've heard the arguments on the moral hazard part, and I just don't find them convincing, in that, as Jan says, we just continue to stay on this baseline path for years and years, decades. And so to say that we're not moving from the baseline because we're too focused on negative emissions, well, I don't know, I guess that would be a concern if we saw we were doing a lot of negative emissions. But what we're seeing is that it's just academic literature for the most part right now, with, you know, with a little bit of deployment. But so I don't know, that's kind of where I come out on the moral hazard argument. But I will acknowledge it's a much livelier debate, I think, to a lot of people than it is to me. And so, yeah, it's good that the question comes up. And Sabine and Jan should also chime in on this one as well.
I mean, one thing I could add is, I mean, I fully agree that moral hazard as such, I think, has not been any relevant at all to explain where we are and where we are moving right now on our baseline trajectory. The question is, could it become an issue? And I find it, Oliver Geden had a recent paper where he mentioned basically the possibility of negative emission targets on the European level. And if you think that in the context of international negotiations, I mean, I would see some scope for moral hazard, because once, you know, parties start to negotiate, like once this possibility space opens, then of course, you know, suddenly new ethical stands that were out of reach can be reached again, like, you know, the compensation of industrialized countries for their historical responsibility. I think that is really, that wasn't clear to me before, I don't know, but it just recently came to me, and I think then it becomes more real. But before that, I really cannot see it. But in principle, I agree with Greg. We are in a situation where we cannot choose, right? We need to do everything, because we are so far off to get anywhere near where we would like to be. And so, from my perspective, emission reductions and the development of capabilities in the field of negative emissions cannot be a contradiction. If it's a contradiction, then, you know, those goals are far, far away from what we can achieve.
Yes, maybe to complement, because I agree with what Greg and Jan were saying, but maybe to complement that a little bit, I think it is also important to, rather than being too scared of moral hazard and the type of moral hazard that negative emissions or the availability of negative emissions could cause, we should probably also focus on why we actually have not been moving on mitigation for the last decades, which obviously was probably not because people had negative emissions in mind, and understanding those factors, which will likely be still barriers in the future for both for mitigation and for negative emissions. So I think there's definitely more to it than just the moral hazard associated with negative emissions.
Okay, thanks. We've got another question on the topic of why we're not seeing the kind of adoption or deployment of nets that we're hearing is urgent. And it's, I think, primarily at Greg's presentation, which talks about the idea of demand from a marketplace, with a lack of demand from a marketplace. And asking whether it might be wise to think beyond those kinds of parameters, instead looking at something like a Manhattan Project approach. Does that seem like a fruitful way to get at nets deployment?
Yeah, that's a good question. I'm glad you raised it. So yeah, we often think about innovation as kind of, maybe you could separate it into technology push, so accelerating the supply of innovation, and demand pull, creating markets for those innovations that are successful. And some of the most successful government innovation efforts in the past, especially from a US perspective, have been the Manhattan Project, which was 5 atomic bombs that were made, and then the Apollo Project, which is about 9 moon landings. And those are completely technology push. It was spending billions and tens of billions on each of those, and there was no idea of markets for them or adoption of who's going to buy, who's going to pay for moon landings, or who's going to pay for atomic bombs. It was all completely just making them available in really small numbers. And that seems to me a model that might seem more like something you might do with solar radiation management, where it could be very centralized and you do a few things in a really big way. But even the biggest nets like BECCS, we're talking about hundreds and thousands of large-scale BECCS plants. And so that's talking about many actors and many adopters. And that's where it starts to, you have to start to think about, even if you don't have a market that creates incentives for those, how you choose how to deploy them, who pays for them, those are all really contentious decisions. And so, yeah, I think there maybe are certain technologies that might be amenable to kind of a Manhattan Project or an Apollo Project approach. But even the biggest nets really are, there's too many actors needed to do that in a centralized way. And then for the smaller nets like soils or forestry, or for the medium-sized ones like DACs, then you're talking about thousands and maybe millions of actors involved. And then at some point you have to somehow create incentives for them. And maybe it's government mandates, maybe it's carbon prices, maybe it's some kind of subsidies, but you can't ignore the demand side. So what we've been so successful at with moon landings and atomic bombs, it just doesn't seem like the right model for any of the nets that we've looked at.
Okay, let's stick with that theme for one more question here. You compared the learning curve for DACs to photovoltaics and to solar cars. Are you asserting that the learning curve will actually mimic the learning curve for photovoltaics? And if so, why?
Yeah, so what I put there was not, learning curves usually have to do with the cost of DACs and the cost of solar. So that example is just really about the timing, so how long it took to get cheap. So I guess underlying it, there is some type of learning curve involved. I think since presenting that slide, I've had a lot of really good feedback from various people about how that comparison works. And so, one aspect of it is the pace of the cost reductions. So, we're saying that that PV was too slow, and that's been by far the fastest learning curve of any other energy technology. So, it would have to be even faster than PV to accelerate it that way. So we have to think about other ways to accelerate this cost reduction and deployment process. I mean, some people are saying that maybe DAX is further along than PV was in the 1950s, that there are starting to be some commercial deployment of it. And I agree, we are starting to see some of that. So that's encouraging. But we also saw that in the 1950s with PV. Like every major country in the world was starting a satellite program in the 1950s after the Russians launched one. And PV was the best way to do that. And yet it still took 70 years to get cheap PV. So somehow we have to overcome that and find ways to make things move more quickly. So I think it's promising what's happening with DAX, but I don't think we can speed up by DAX by having a faster learning curve. I think it's got to be more on the market side, and we got to start building some of these facilities, start getting real commercial operations to pay for them, have real customers. That'll improve them. That'll achieve scale. That'll get the learning curve going. And then if we start seeing that in the next, say, 5 years, then I would be much more optimistic that maybe we can break free from that long time timeline that PV has taken and do something much faster.
Okay, great. Let's move to a different topic then, non-CO2 greenhouse gases. What does this survey that you've done of the NETS literature show about the role of NETS or connection between NETS and non-CO2 gases like methane?
So actually, the non-CO2 removals, or the removals of non-CO2 greenhouse gases, was not part of the systematic scoping of the literature. We did come across a couple of articles which we then discussed in the end of the article, but they weren't featured in the type of potentials and cost assessments that I've been showing. I think it is a very important emerging field because these are particularly emissions that are very difficult to get rid of and that are also associated with, for instance, the production of food and so on, that we cannot of course suddenly decrease quite drastically. So I think this is actually what some of those papers that we've been discussing before are trying to do, to also have diet shifts so that we see less livestock and so on. But I think it's definitely also a promising avenue to think about how to remove those GHGs, and there are a couple of people working on this. So this is something to definitely have an eye on in the future. I don't know whether the others wanted to say something on that as well.
I think that covers it.
And related question then, how do uncertainties or differences in projections of non-greenhouse gases or non-CO2 greenhouse gases and aerosols affect the role of NETs, of specifically carbon removal, in these scenarios?
Maybe we can answer that question in terms of carbon budgets, right? So we see now a lively discussion around carbon budgets, where the budgets coming forward from the IPCC AI5 maybe on the tighter end, and maybe there is some space. And as I understand it, but this is really not my field, one component of this is actually that if you consider a much richer set of scenarios where that explore, or if scenarios that explore different mixes of non-CO2 gases, you actually have more flexibility in your budget. And if you have a larger budget, then vice versa, keeping everything equal, you are less dependent for the moment on negative emissions, so you have a little bit more room. So this is how I would see this.
Okay, thanks.
But maybe it's worthwhile to also say that this is still also under discussion and will be also something that will be coming forth from the new special report and so on. So it would be actually instructive to also wait for that debate to take a bit more foot.
Okay, let's go back to models for a little bit. Parts of the discussion that we've had today sound like integrated assessment models are being treated as evidence, right? So we've heard the phrase scenario evidence at least once. But of course, these are constructions that involve lots of difficult or controversial assumptions. So can you say a little bit about how you perceive your role as researchers working with models and the scenarios produced using them? And how do you think about or ensure a democratic discussion of the assumptions that go into those models?
I think one of the things we need to become better at is actually discussing those assumptions, and I think that is really really important. But at the same time, it's really difficult because these models are so large and complex, right? So which aspect are you starting to discuss? I was involved in the 5th assessment report, and we wanted to do a good job in that, but it's really tricky. I think in terms of dealing with that evidence, I think I find this discussion very hostile, and my answer is always, horses for courses. We can learn something from those, and we need really to be, at the first level, look at the scenario, like the major scenario assumptions. What are they doing on what institutional assumptions do they take about, what kind of policies are happening? Secondly, on the technology level, what's in there and what's not in there. That's an important decision, right? We learned that in AR5 as well, where people were upset that they didn't realize that now BEX was added, and some people felt, it shouldn't be added. And if we add it, then you better, rather than saying it's part of the default scenario you're comparing against, you rather have you rather have a default scenario without BEX, and you have a scenario plus BEX, which gives it a completely different which makes a completely different communication. And I think these things are something we need to learn. I think we also need to learn to have much more stakeholder engaging processes in the design of scenarios. But otherwise, I really think they are what if explorations of the future. They are not predictions of the future, and we really need to ourselves, to take some time and understand what they are trying to do, and then I think we already go some way. And on the other hand, we know some of the dynamics we always observe in those models, and I think that's institutionally they are like fantastically optimistic in terms of what happens, in terms of global carbon price, etc., etc. But what we often forget is that they are often also a bit pessimistic on the technology side. So, for example, on solar PV, we have seen papers where actually they show that the learning is much faster than represented in those models, and I think that's also something that somehow balances off, or we need to look at more often. I don't know the answer for that, but I think in principle they serve a role and we can understand them. And but of course, a much more participatory way of engaging on these scenarios, I would also really welcome.
Yeah, and I just add a couple of things to Jan. So I'm sympathetic to the comment or the question that provoked this here. And yeah, I think part of it is this trade-off between complexity and transparency. And the models have gotten so complex, not in order to hide things, but in order to be more realistic and take into account things that, like non-greenhouse gases or aerosols or new technologies that people have complained were being omitted. And so as these new features are being added, the models get more complex, and getting a clear answer about what's your assumption about the cost of carbon capture in 2030, there's not an easy answer to that. And the part of it that comes up with that answer is code that's buried in a lot of complexity. So that's just kind of where we are in the models. I think one reaction to it that you can see in our results is to use lots and lots of models and many different scenario runs. And so instead of having a a path or a line that we use these fans of uncertainty. And I think for a lot of people, it's hard to process that much of uncertainty, but that's, I think, a pretty close approximation of the reality that we know. But then, yeah, and also I think to Jan's point, these models do provoke discussions. They provoke people to say, hey, you're missing something and that needs to be included. For us, they've provoked, all right, all these models assume lots of nets. Let's really look into what's real about them, what the literature says, how ready are they, how scalable, what are the costs, what are the resources available. And so I think that's a good discussion to have. And then even this one we mentioned a few minutes ago about these low energy demand scenarios, that's another response to models that seem to assume lots of nets and assume lots of growth in energy demand over the century. And so I think that's a healthy thing to say, well, what happens if that's not the case? And here's a whole set of assumptions where people live more in cities, people switch away from eating meat, people use more sustainable transportation, a whole set of assumptions that leads you to have lower energy demand. And then you can take a look at that, and I think Jan gave an answer that I would kind of share too, to say, well, it does look like that's possible, but it looks like a really different world than we're in right now, and even where we seem to be headed. And so that's also kind of a reality check as well. So yeah, I think there are uses for models. They're not a prediction of the future, but I think they do provoke discussions, and that's what we're using them for.
Yeah, and maybe just to complement what Greg said, I mean, it's true that one of our motivations was also to complement this evidence coming from the scenarios, to compare those pathways to what we actually see from the bottom-up literature. And I think that the integrated assessment community has also been responsive to these kind of findings. For instance, to the whole criticism around the large-scale deployments of BECCS. So not only in terms of those scenarios that Jan and Greg have been mentioning, where you have drastic reductions on the demand side, but also you see a couple of models now that integrate more than just BECCS. And what you actually see is that, for instance, the land footprint can be reduced then. So this is why we think that by showing that there are a whole array of opportunities of CDR options that could lead to negative emissions with different side effects as you scale them up, that could also imply that if you deploy some of them, maybe even in a synergetic way, to some extent only you could minimize side effects and still achieve some negative emissions that you might need for locked-in emissions or committed emissions, or also for those sectors we've been talking about that are difficult to decarbonize.
All right, thank you very much for that, Sabine. I'm afraid we have reached the end of our hour. I apologize to anyone who wasn't able to get their question in, but I'm hoping that you will continue to participate in future webinars and where these questions might be also pertinent. So at the outset, I'd again like to thank all three of our participants, Jan Minx, Sabine Foose, and Greg Nimet, for taking the time to share their insights today in terms of their respective articles. In upcoming webinars in this series, we'll be joined by additional experts who will look at a number of different specific carbon removal negative emissions options, including bioenergy with carbon capture with storage, the carbon removal potential of soils, direct air capture, as well as ocean-based options. In each case, we'll seek to present a range of views and perspectives in terms of technological possibilities, environmental and social risks attendant to these technologies, and issues associated with governance of research, as well as potential deployment or adoption. Our next webinar will focus on the prospects for increasing soil sequestration of carbon, and it will take place during the week of July 9th, and we'll announce the specific date very soon. All webinars, including this one, will be archived at our website, which again is ceassessment.org. And so again, Thanks to all of you for joining us. My name is Will Burns, co-director of the Forum for Climate Engineering Assessment, and we hope to see you again in the future. Goodbye for now.